Okay, now we're gonna work for part 4. So part 4 is just gonna be doing 12 steps basically inside a for loop, and we're gonna start from 0. So basically when it says start again as in step 2, it just means start from 0. So we're not gonna take any of our old y minuses or y pluses to begin to solve this problem. So we're just gonna start from 0. The first thing that we want to do is set our time equals to 0 because we're starting a new run. Next thing, give your y naughts, which I believe are going to be the same thing as the ones you used initially, so we can just copy and paste that y naught. Now the next thing that you have to do is that we're going to be making a for loop that is going to have 12 steps. So we're going to go from I1 to I12, and I'm pretty sure you remember just how to do that. Just make sure it goes from I1 to I12, and then we're going to end our loop and then just start filling in the loop. So the first thing that should go in your loop is your ODE equation. So just remember that your ODE, let's just make it here, t, y equals then ODE 45. Whatever your function is that contains the walker. Now your t, then your y naught, and now your OPT. So something that you have to modify for this new one is, first of all, your time. You have to be able to, so every time we run through the loop, we're going to run a different step. So we have to make sure that every time we run through the loop, we update the time inside our ODE function. So in order to do that, we're going to start from time equals to 0, right? And then it's going to be 0 to 5, right? Then we're at the end of the for loop, we're going to change this t naught to be the end of the previous step, so that at the beginning of the next loop, so when we run this again, we're gonna have an updated time. So basically what we want to do is just add t naught to our initial time. What this is going to do is that for the first step, t naught is going to be equal to 0 because we defined it here. So it's going to be 0, so it's going to be 0 and 5, but for the second loop, t naught is going to be the end of the first step. So just remember, if we want to update t naught, we need t, and then we need t of the end of the first step. So I'll let you fill that one up. We can let that one be our last line, so we're just going to continue filling it after our t. Now, if you look at your description of the problem, it says that you want to accumulate all the solutions in a vector t and a matrix y, one step after another. Basically, what this means is that at the end of your run, you want to accumulate your t's and your y's into a t and y vector. In order to be able to do this, we have to change the name of the one here, just because we're gonna use t and y to be like our save vector. Basically, we're gonna save all of our t's and all of our y's inside t and y. So then we have to change this name to whatever you want it to be. We can call it t old or t new. Let's call it t mix. Makes a little bit more sense. Or t2. Let's go for now t2 and y2. Now, now that we calculate t2 and y2, we want to actually accumulate it into our t and y vector. And to do that, we're going to do the same thing that we did last time, which is just say, okay, so I wanna keep on adding things to this vector. So we're just gonna use our t, which we have to create outside the loop because we're gonna be using it here, and now we're gonna say t new. Since we did this, since we are first, so when it's gonna run the first time, t right now it's nothing. So we have to make sure that we create it outside of the loop. Otherwise, when it goes through the first step, so the first step is the only really problematic one, because when we go through the first step, it's gonna look for t, but it's gonna find nothing. So we just have to create an empty vector for t so that we can it's just going to be, okay, we have nothing here. Now your first value of t is going to be, or your first set of values of t are going to be your t new. Now when it runs the second step, your t is going to be your older t, or not t new, but t2. Sorry, you can call it t new or t2, it's up to you. Now for the second time, your saved t is going to be t, and then your t2 is going to be your second step t. So if you think about this very carefully, t2 is changing every step. And to make sure that we don't lose that information, we're just saving it into our time vector. And then go ahead and do the same thing for y. So create an empty y vector out here, and then create a save vector y down here. So basically that's going to save all your t's and all your y's. Now the next thing that you have to do is to create your y minus and your y plus. And this is because this is what you need to make the initial condition. So basically, if we go back here to our equation 5, we see that this theta of tau minus, phi of tau minus, this is basically just y minus. This is y plus, and this is a. So what we want to do here is basically just copy and paste what we had for y minus. So we do y minus is equal y new end comma colon, and then apostrophe, don't forget that. So let me just write down here so that we have clear. So we know that y minus is all of the last values of our y. So which y? This y2. So we're going to say y minus is equal y2, and then we want all of those last values, which are going to be the end values for all the y, and we want all of the columns because we want theta, phi, d theta, dt, and then d phi, dt. So we want all of them. And then, as I explained to you in the last video, you have to put what is this? Like an apostrophe, so that you can make it a column vector, because if you just leave it like this, it's going to be a row vector. And if we look at our equation 5, we need to multiply 8 times a column vector, not times a row, times a column vector, yeah, not times a row vector. So we need an apostrophe here. Now that creates our y minus. Then go ahead again and calculate your c, how we did in the past. Then you can go ahead and calculate your a. And then finally calculate your new y naught. Basically, your new y naught is just going to be the same thing as y plus in the beginning, but we just call it y naught here. You can call it y plus if you want as well, but we're gonna call it y naught here, and it's the same y naught here. So here we're basically updating our y naught. We're making y naught y plus here. And what is y plus? Y plus is a, the a that we just created, times the y minus we just created. And this is the same thing, our y plus. I'm just calling it y naught because it's just basically our initial condition. So we are making that the final conditions of the first step become the initial conditions of the second step by multiplying it times our matrix A. Now the last thing that you need to do is to find tau. So tau is going to be a vector that is going to be growing one by one. So basically we're going to say tau of I, so that the first tau is going to be the time it takes for you to give the first step. Then tau of I equals 2. So on the second run, I is going to be equal to 2, and tau 2 is going to be the length of the step of the second step. Okay? And I'll leave it up to you to calculate this. Just know that tau is the end time minus the beginning time of each step. So once you find all of these tau, they should all be around, say, 3.8, 3.9. They all should be pretty close. If you get values like 7, like 3, 7, and like that, is because you're subtracting the wrong number. You want the length of each of the steps. So I'll let you think about that. Now, I think that's all you need to have inside your loop. So it's your differential equation first, then your saving terms. You need a t and you also need a y. And then you need to change your y minus into y plus. To do that, you make y minus be the end of y2. Then you make your c vector. Then you make your a matrix. This is basically just a copy from the part before. And then you make your Y naught, which is just the same thing as your Y plus, and then your T naught, which is the same thing as your T end. So this is just going to be T end the last time, so that every time you loop, you're up the same T naught. The only thing that's helping you to do is to update the time inside of your ODE. Let me think. I think that's it. Then after your for loop, then create a variable that is called period, and then print all of your taus. Then you can just say period equals tau. Basically, that's all you need to do. And then just plot it the same way we have plotted things before. The same thing, you can just copy and paste the same plot equation. And then it should look like an oscillation that starts at 0, of course, and ends about at 46-ish. And it should look like oscillating. Now, I think that's all you need for part 4. Please feel free to email me if you have questions.